So from now on, we'll be talking about several topics. So today we're going to be talking about iterative methods for large-scale problems. We'll show that why do we need them? Because the amount of computation, if you don't use iterative methods, then the amount of computation you have to do scales superlinearly with how many grid points you put into the problem. So if you increase the problem by a factor of 2, the amount of computation, how big the computer has to be, increases by a lot more than a factor of 2. And iterative methods seems to be the only way out of this. So when you have a very, very large problem, using iterative methods seems to be a lot better than using a direct method for example, for solving a linear system. If you have problems like the ones in our project, it doesn't really matter. Probably for some of them, direct methods are even faster. And then we are going to be talking about error estimation and uncertainty quantification. We already talked about how much error we are introducing in our numerical techniques. But we are going to be talking more specifically on, can we actually get a numerical value associated with the outcome computed in numerically solving a PDE. So we know that in every experiment, a good experimental result would have to include an error bar, right, in whatever data you get. And why shouldn't we do the same with numerical methods for solving PDEs? There are errors everywhere. There is error in our numerical methods, right? We're approximating things. So that is traditionally the method of quantifying how much error is due to the numerical methods are usually called error estimation. But there are also errors due to other things, like the geometry. You may not get in the perfect domain that are corresponding one-to-one to what is physical. If you're solving structural problems, you may not have exactly the right material properties. You may not have exactly the right boundary conditions. So dealing with trying to quantify the sources of error coming not from numerical solution itself, but from specification of the PDE is usually called uncertainty quantification. But I see they share a lot of common characteristics. And 3, we are going to be talking about optimization. So sometimes we solve a PDE just for the result of it. That's a lot of times that's the case in scientific applications. And there are also many cases we want to solve a PDE not just for this specific problem, but just to design the problem itself. If we want to design an airplane, we actually don't have a geometry to start with. We want to solve the PDE for the purpose of changing the geometry to make it better. And even in scientific problems, there can be parameters you want to estimate that you don't know. And you can only estimate the parameters by assuming the parameter is that value, solving the PDE, compare the results with experimental results. And if it doesn't match, that means your parameters are probably not right. And then how do you actually tune, or in the mathematical sense, optimize the parameters so that you have the best optimal match between numerical and experimental results? That's another optimization problem. So how do you use PDEs to do optimization? And the primary technique we're going to be talking about is adjoint, or in the more modern kind of machine learning jargon, it's called backpropagation. But they are the same thing. There is just a difference in name. And something I haven't decided. If we talk about the first 3 in 4, we probably don't have time to talk about is a complex spatial domain and unstructured mesh. That's usually in the context of either finite volume or finite elements, and also parallel solution of numerical PDEs. And that's becoming more and more important nowadays when there are just you have so many machines available, either in your lab or in the cloud or in a supercomputing center, that solving your problem on these computers is basically almost qualitatively different from solving it on your own machine. So I want to get and also there is potentially one lecture on using console to interactively model problems using PDEs and solve them with not much coding by yourself. You still need to derive the weak form because console is based on finite elements. So for every problem, you have to know how do I derive the weak form, how do I integrate whatever boundary condition I have into the weak form, is it essential or natural boundary conditions. But once you have the weak form, you can basically give it to the software and ask console to solve it. So I want to get a sense of just a raise your hand from people. How interested or how useful do you think each of these topics are? So iterative methods for large-scale problems. So a lot of you wants to solve large-scale problems. And by the way, if you go to parallel solutions, it's direct method usually works a lot. I mean, iterative methods usually works much better than direct methods if you go parallel. Area estimation, uncertainty quantification. Still, most of the people. Okay, optimization and adjoint. Wow. Okay, complex domain, unstructured mesh. So that's a lot less, about between a third and a half. Okay, parallel solution of PDEs. It's like more than half. Okay, interactive PD modeling and simulation using console. It's like a quarter. Okay. So I'll keep in mind of the request by people, particular. So the first three seems to be covered for sure. The parallel solution. Let's see. So I'll look at the schedule and figure out if we can spare a lecture for that. All right. Okay.